Happy New Year everyone, and welcome to another episode in which I try channeling my inner child and continue playing with soap bubbles. This is what we're going to build today, a bubble triplet. And this setup is something special to me. It was the first algorithm that I implemented, not exactly from a scientific paper, but from a paper-ish writing, which through a lot of cursing taught me a lot. And after all those years, I think it's time to revisit that algorithm and rebuild it in Houdini. So this setup comes from Andrew Glassner's CG&A columns. Andrew Glassner is a computer graphics author, publishing books on rendering, general computer graphics, or neural networks, but also around the turn of the millennium, he wrote a column for the CG&A journal, that is Computer Graphics and Applications. And in here, he explores a few interesting ideas, bit of original research, and fun projects. And down here he has two columns on soap bubbles, of which we're going to read the second article here, which is this. And the first part of this article deals with interference colors, which is what we built in the two previous videos. But then this article continues and explores the science behind how bubble clusters, that means bubble triplets, form. And I think this article is a good preparation if you're planning on dealing more with scientific papers, if you want to implement some algorithms. And I think this algorithm is really good as kind of a stepping stone, kind of a ladder towards being able to read and implement papers. Because this article is very legible, very understandable, very readable. It also comes with good explanations and good graphics. And in the end, it even has some pseudocode for us to implement. So if you want to get into what it feels like reading and dealing with computer graphics papers, I think Glassner's columns are a good bridge towards those papers because they're easier to understand, more accessible, and very rewarding to go through, while at the same time teaching you valuable skills which will be useful when later dealing with quote-unquote proper papers. So what's the deal with bubbles? Let's have a look at this image here, which is a cross-section of two bubbles meeting, a bigger and a smaller one. And this is the inner wall of the bubble. And the funny thing about the behavior of soap film is that when three soap films meet, such as in this area here or down here, the angle between two of those films, for example that one, the outer hull of the bigger and the outer hull of the smaller bubble, form an angle of exactly 120 degrees. So the angle between those surfaces here, and those surfaces here are exactly the same, 120 degrees. That is exactly what Glassner illustrates in this diagram here, where those tangents, tangent A, B, and C, with A being the larger, B the smaller bubble, and C the inner wall of those two bubbles. And in this point M, for example, all those three tangents have an angle of 120 degrees in between them. And with a bit of clever geometry, Glassner in this article works out the relationship between all those individual points necessary to create the 6 spheres that we will need to build a bubble triplet. So why do we need those 6 spheres if we're only interested in a triplet? Well, that is because we also want the inner walls. For example, in this very 90s rendering of soap bubbles, you can see not only do we need those 3 spheres to create the bubbles themselves, but also those surfaces that form the interior surface are 3 other bubbles that have been intersected with our main bubble spheres. And while typically a scientific paper might just end with the relationships of those individual points and these spheres radii, Glassner in here even provides pseudocode, which means it's computer code that is not really computer code. It looks a lot like C or C++. However, it's got some functions, for example, sphere, where we're just passing a center and a radius, and then our program is supposed to just create a sphere there, which might not be a command or a function in any programming language. The same here, where he's using constructive solid geometry. That means, in our case, let's translate this as Booling to build the outer sections of the bubbles and the inner walls. So let's put this on the side and start Houdini. And let's go through the pseudocode here and build our setup in Houdini. So I mentioned that Glassner here uses a command called sphere to create those 6 spheres that we need later. And inside of Houdini, what I'd like to do is, instead of creating those spheres, is just create a single point for the sphere's center and then saving a radius. In Houdini lingo, that will be a p-scale attribute on this point, as well as the sphere's name, which will later be drawn around the center point. Then up here, in the first 3 lines, we're seeing some helper functions, which is the first thing we're going to implement. So in Houdini, in the OBJ context, let's just drop down a geo node, dive in there, and then let's drop down an attrib wrangle, which we're going to set to run over the detail. That means only once. All this code that we're going to write will be executed just once and not for each point. So let's get started with this code up here, which are some helper functions. So let's just copy and paste this over here and reformat it. And as I've been mentioning, this is pseudocode, and you can see that most of the code actually is not been highlighted by Houdini, so it's not correct VEX code, and I didn't expect that. Some functions, such as the square root, are indeed recognized, but let's work on those. So each of those lines should be an individual function. So let's start with the first one called getR. Let's declare this to be a function, and it should return a real. Well, in Houdini, we do not have the data type of real. The closest thing we could be using would be a float. This is the function's name, and in here we have the function's arguments. So this takes in a real, which again we do not have, so let's substitute that with a float of r and one of small r, like this. And then it should return this value here. So to do that, let's just go into a new line and enter 2 curly braces, and just take this line here, move it up here into those curly braces and indent it. And this is what the function should return. So let's just specify this as the return value. And now this function here is exactly the same thing as the first line here in pseudocode, just written in VEX. So I'm telling VEX I'm declaring a function, which is going to return a float value. This is the function's name. It takes 2 arguments, capital R and R, which are float, and returns this value here that we're going to calculate down here. Do the same thing for the other functions. So that's getD. And finally, the last one. Like this. Still getting an error here. Let me check that. And yes, misspelled function there and missing a return here. All right, so these are our helper functions. Let's just do a bit of ASCII art here. And then let's work on our main code. So first 3 lines down, another 57 to go. So the next thing, this make bubble function here, this is the main function. You can see it starts here and line 5 ends in line 60. And some of that stuff, namely anything that happens after we created those center points here, we'll be doing in SOPs. That means using standard Houdini nodes. So it's a measly 36 lines that we have to take care of. Okay, so what this says is that the 3 radii of our main bubbles, RA, RB, and RD, which is what specifies the individual diameters of those 3 bubbles here, they should come in descending order. That means RA is the radius of the biggest bubble, RB is the radius of the intermediate bubble, and RC is the radius of the smallest bubble. For now, I'll just create 3 sliders. And I'm just going to make sure manually that RA is bigger as RB is bigger as RD. So CHF is a float slider. Let's call this one radius A. Copy this line, paste it twice. I'm going to call the other one radius B and radius D, respectively RB and RD. Now we'll encounter one commonality between some of those papers, especially early computer graphics papers, and with early I mean like 70s, 80s computer graphics papers, is they use very short variable names. And this might either come from those diagrams that the researcher or the author of the paper drew up and just sticks to her or his convention, or to be more economic so you don't have to type out those long variable names. Let's just start by creating this DAB here. So in here in Houdini, I want to create another float. Call this one D capital AB. And it's equal to, now we're calling our first helper function, the getDist here. So getDist, passing along 2 arguments, RA and RB, like this. Next, let's create RC here, using another one of our helper functions, getR, and passing RA and RB into it. Next, it's DAC, so I can just copy this here. Make sure there's a semicolon at the end, and also copy these 3 lines here. Tired of typing those out, just making sure I'll end them with a semicolon. And make sure that they're afloat, and get rid of the line numbers here. Like so. Okay, still running. Next 3 lines, and again, all of this looks a bit more complicated than it actually is due to the naming conventions and due to us not having gone through the exact origins of those diagrams here. And if you're interested in finding out how Glassner actually came up with his reasoning behind those formulas, I urge you to read this article. It's highly readable, actually quite enjoyable. Okay, we've been stuck here. Let's paste those down again, make sure they're afloat and finish them with a semicolon each. getting rid of the line numbers. Like so. Next, we're doing a bit of trigonometry, rotating a few points in space. So let's have a look at how the pseudocode is written here and how that translates into Houdini's VEX. So we've got the theta A and the decenter here. So let's break them up into floats, which end with a semicolon, getting rid of the line numbers and ending those with a semicolon as well. And theta A is fine. This is just a single float value, the result of the arc cosine of this weird expression back here. However, the decenter, that actually is not a float, that is a vector. And the way this is specified here in this pseudocode is just with those square brackets here. However, in Houdini, we specify this with a set command and then the normal parentheses. And also in Houdini, this vector is a vector of 3. So not only has it an x and a y component, but also a z component, which we're gonna be setting manually to be just 0 for now. Okay, next is this one, and I'm seeing a vector in here again. So that's gonna be a float value. And we'll be normalizing this value here. And I honestly don't know why you would want to do this, subtracting a vector of 0, because it doesn't do anything to your calculation, subtracting 0 from it. And of course, again, it was to notify me as the reader to pay attention that this should not be a float, but a vector, like this. And also we can get rid of this here. Just testing. All right, move on to this one, which, judging by the brackets here, is a vector as well. So let's paste that in here. Can get rid of that here onto those two lines here. Again, finishing them off with a semicolon, getting rid of those line numbers. And this should be a vector as well as this one here. And in here again, we find those square brackets, which is a notation which we don't know in Houdini. So let's use the set function instead and make sure it's a vector of 3, setting the z component to 0. F-center here is the same thing. So let's use the set function, making sure it's a 3-element vector. Now, finally, we're here where it gets funny, making those individual bubble spheres / their center points. So let's just copy those 6 lines here. And also let's just make a comment. Make bubble centers. Paste this here. Getting rid of those line numbers. And as I mentioned, what I want to do is I want to use Houdini's SOPs to do lots of this, creating the spheres and intersecting them. In fact, I want to use the copy to points node to copy a sphere onto those center points here and scale it by the radius that's stored on the respective center point. And also, I want to make sure that my sphere has a name. And I could store a name on my geometry as a string attribute, or I could use a group, which I call BA, BB, and so on, which are 2 or 3 lines of VEX. However, I do not want to have those 2 or 3 lines of VEX appear 6 times here. So instead what I'll do is I'll create another helper function up here, which I'll call sphere. So let's call this function sphere, and it's going to be of type void, because it's not going to return something. It will create points on our geostream and not return any data. So this takes as an input a vector, which I'll call center, or let's call this one pos for position. It's going to take in a float, which we'll be calling radius, and a string, which I'll call name. Now let's create the actual function in here. And of course, that one was the wrong way around. Sphere is the name and void is the data type, like so. Okay, let's create the function. So I want to add a point at this position here using the add point function. And let's call the new point new PT. Just storing this new points number. Want to add this to the geostream I'm currently working on, 0, and I want to add it at the position pos. Next, I want to create an attribute which stores the radius on that point, and typically radii in Houdini are stored in an attribute called pscale. So let's create that, and setting it using the setPointAttrib function. So on our current geostream, we want to set a point attribute called pscale on our point new point, and it should have the value of radius. So we're just pushing this radius value into a point attribute called pscale here. And finally, we want to create a point group called name and tell Houdini that this newly created point is part of that point group using the setPointGroup function. Again, on our current geometry, the point group's name should be name. And into this group, we want to put our new point called new PT, and we want to set this group relationship to 1. So now this point is in this group called name. Okay, let's fix those errors, which stem from the pseudocode down here, and we have to rewrite this. So I'm calling my sphere function with the center point, which is all zeros here, and should have the radius RA, and its name should be BA, like this here. So like this, and a semicolon. Let's just check by commenting out the other lines of code down here if that worked with a single point. And yes, we can see in the middle here in the center. Let's just hit D over the viewport here, go to geometry and increase the point size here. Yes, we can see we created this singular point. Let's make the background dark here. Also, let's just make this full screen and go to the geo spreadsheet here. Setting that p-scale does not seem to have worked. However, setting that group has worked. And of course, this p-scale is still 0 because up here where I created those sliders to dial in the radius, I didn't actually create user interfaces for those and didn't dial in those values. And to do that, I'll just click this button here, and now we should have 3 sliders. Where are they? All right, Houdini being a bit weird today. Let's create those sliders manually by going to this cogwheel symbol, going to edit parameter interface, and then let's drag out 3 float sliders here. Call one radius underscore A, call the label radius A, should be the top one. Let's call the middle one radius underscore B, label is radius B, and the last one radius underscore C, and the label is radius C. Bit tedious. Usually the shortcut with this here works. However, in my Houdini version, apparently there's a bug. Hit apply and accept, and you're presented with those 3 sliders here, which still isn't working because when I hover over this, I spelled my parameter radius underscore A, not containing any capital letters. So let's change that up here. Like so, and finally we can see we're getting this p-scale value written on our point. Let's just dial in some values here, 0.6, 0.4, and I don't know, 0.3, like so, and take care of creating the other sphere centers here using the same syntax as we did here. So let's just copy, paste this one being the sphere BB, this one here, it's got its radius RB, and is centered around DAC, no, it's DAB actually, and 0 and 0. All right, that's been this one here. Next is this one here. So again, just copy this. That's its name, and this. Let's convert this to Houdini syntax, like so. Semicolon at the end, and 3 more to go. So same procedure as with the previous one. Just let me check. Actually, we're at BD here, so that's this one here. Goes up here. Call this one BD. And let's take those last 2 as well. This one's called BE. This one BF. All right, where did we go wrong? This is a semicolon. All right, and you can see we created a bunch of spheres here. And if we change the values here, those spheres move around. All right, let's just check for their p-scale value here. And yes, that is mostly fine except for the last 3 we just created. So let's check on them. So RD, RE, and RF, that's where we're going off. And after having stared and cursed at this for a while, I made a small mistake. So up here, where I'm reading the last radius, specifying radius D here, although I called it radius C. So let's fix that by going back into our parameter interface, and it should be called radius D. Like so. So apply and accept. And let's dial this in here. Check again. And to make this refresh, I just deleted this underscore and repasted it in here. And now we can see our p-scales are all there. So finally, we're ready to progress here. And what you just witnessed, this tiny mistake here in just renaming a variable or misnaming a variable or an interface element, is one of the major sources, at least with my code that I write or with my setups that I build when it comes to debugging. So sometimes it's actually the very mundane stuff like user interface or variable naming that will get you and bite you. Right, have a look at the scene. All those points are here. Let's just use the copy the points. points go in this slot here and drop down a sphere to instance those spheres and set their primitive type to be a polygon and increase their frequency a bit. Before we do that, let's just for good measure save this, wire this in and highlight it. And let's disable our numbers here. And that does not seem right, which brings us to the second source for errors. And that is actually misprints in the paper or maybe different coordinate systems in the paper. So after experiencing something like this, what you can do if you're sure all your variables are named correctly is either, again, go through this paper and its source code and maybe try to find out its reasoning and check if the source code provided here matches with the geometry and the formulas drawn out here. Or if you're like me, you just start poking at the math here and find out that the first component of our D-center has to be negative. It still does not look 100% correct. That is because we're also having those very large bubbles in here, which we will be using now to cut out those interior walls for our bubbles. So all this, what's called CSG here, constructive solid geometry, is what we'll be doing using booleans in Houdini. So when we middle mouse on what we've seen here, we can see that all of those spheres have their points grouped into those group names, which we specified up here for those individual spheres. And also I misspelled this group name here, so let's just fix it like this. All right, so those individual outside sections are as follows. Section A equals to our bubble A minus the union of our bubble B and D. So let's set that up. As we'll be doing this about 6 times, let's start with a null. Call this one in. Wire now copy the points in here, and then let's drop down a boolean. And our input slot goes into the left thing here. In our boolean here, I want to take the union of bubble B and bubble D. And I want to treat both of those bubbles as a solid. And when I try and drag down this group selector here, I can see that those groups I created with the bubble names aren't shown here. And what I could do to resolve this is either try and promoting those point groups to primitive groups, and then those groups would show up here. Or, which I found more reliable actually, is using blast or delete nodes and make sure that we are deleting the non-selected geometry in here, wiring this into their respective input slots into the booleans. And then in the first one, let's select our BB group. In the second one, our BD group. And now we can see we're creating the union of those two solids, BB and BD. Now we want to subtract this from BA. So again, let's copy this node here, paste it. This time switching it out for BA, so that's this one here. Dropping down another boolean, this time subtracting A minus B, so B goes in here. We want to treat B as solid, and A we want to treat as a surface now, so as a thin film. So now I can see I cut this hole into my first sphere here, BA. To this, let's attach a null, like so. And as we'll be using this 5 more times here, this construct, let's just push it to the side and maybe let's create a network box around this, calling this one CSG, constructive solid geometry. Okay, let's take this box, copying and pasting it. So now we're at this second sphere or second section here, section B. So that is B minus BA plus BD. So that's this one here. Okay, again, moving this to the side, copying this, pasting it one more time. Now we're at this third line, section D should be equal to BD minus BA, already selected here, plus BD. BB, that is, beta. Okay, and if we merge those 3 sections here, we can see these are the outer shells of our bubble triplet. Everything fine so far. Okay, let's take this one, copy and paste it, and work on the inner walls here, the remaining 3 sections. So in here, what we want to do is we want to select anything of bubble C that's inside of bubble A, and from it subtract bubble D. So to do that, let's rewire this a bit, just deleting those 2 booleans and starting off with a new boolean. And the first thing I want to do is I want to intersect a surface with a solid. The solid being BA here, and the surface being BC. So that's this one here. And from this, using another boolean, we're going to be subtracting, and again, the first one is its surface. From this one, we're going to be subtracting BD delta, like this. And this is our output. So let's take this and copy and paste it again, taking care of this one here. So it's BE epsilon inside BA, that's this one here, minus BC Charlie, like so. Let's copy and paste this one more time. Working on this last section here. Again, this one needs a different wiring, so let's drop down a bool. And in here, we're going to be intersecting two solids, namely BD and BE. So this one is B delta and this one B epsilon, and dropping down another Boolean set to intersect, this time between a surface, which is BF in our case. Goes into the first slot. The result of our other Boolean goes into the second slot. Let's highlight this, wire this into our null here, and also merge those three inner walls. Check. That is looking almost right. Something's not correct here with our very first wall here, which is this one. So again, let's diagnose. And in this case, it turns out that we do not have to subtract B delta as given here in the pseudocode, but B epsilon like this. And now we've got our inner walls here. I'm not sure if this is a typo or if this is due to the changes in coordinate systems, but I think it might be a typo here actually. All right, inner walls, outer walls, we could either merge them using one single merge or just building a tree of merges here. And now if we switch to wireframe, hitting W over the viewport and just maybe full screening this, we can now see we have both our outer spheres and our inner dividing walls. So quite elaborate setup here with those CSG nodes here, the Booling makes it look more hefty than it actually is. Fiddly part here is translating that pseudocode into VEX and making sure that you're not doing typos yourself and you catch those two typos that were in the original article. Apart from that, we can now dial in our sphere size. And yes, the Boolean takes some time in here. We can see we're getting somewhere. As mentioned, these three radii have to be ordered in descending order, so biggest one first, smallest one last. If that doesn't happen, the whole setup breaks, so now the inner wall here is anything but correct. And in order to make sure that this is always the case, you could, for example, add a bit of code up here after you read in those three radii and make sure that this variable is always the largest one and this is always the smallest one of those three input variables. But that is it so far. If you want to shade this with a nice soap bubble shader, you might want to look at our last two videos in which I'll go over building those shaders in Octane or Mantra. And we also do have a free giveaway of a shader I built in Redshift that also does thin film interference. So those soap bubble streaks. And if in general you want to support us or learn more about Houdini, consider becoming a patron of ours. You'll get access to more in-depth courses, not only covering Houdini, but also Unreal Engine. And for all of you already supporting us, thanks so much. Without your help, Intagma would just not be possible. With a very special thank you going out to Patrick Fillion, Important Looking Pirates, Rafik Anadol, and Chris Hebert. Thanks so much, guys. So, until next time, it's cheers and goodbye.